Historical geology students, this is the last week of lectures, and after this week, we're going to have a final exam on Monday, May the 3rd at 7 p.m. That'll be the end of this class, unless I see you this summer in physical geology class. Also, the final lab quiz will be due this week, and I'm going to prepare those for you and send you information on that soon. Last time we were talking about chapter 17 and glaciers. We talked about the pleistocene epoch, 2.6 million years ago to 10,700 years ago. That was the last ice age, and it left behind these things called moraines, which is really a French word, marrons. And what is a marron? Well, it is shown right here in this photograph. See how this ice has this black streak in it, and over here too as well? That's glacial till. And glacial till is poorly sorted. It usually is preserved as either breccia or conglomerate in the rock record. And these ridges of till are called marrons. The ice forms these marrons. So how do we know what parts of the earth were covered by ice in the past? One of the things we look for are these marrons preserved in the rock record. This glacial till, T-I-L-L. Other things left behind by the last ice age include the Great Lakes, Lake Superior, Lake Michigan, Lake Huron, and Lake Erie, which are near the border with Canada. These were carved out by the ice during the Pleistocene epoch. These are large glacial troughs. After the ice melted, it filled these glacial troughs with water, and these are all, as you can see here, formed during the ice age, towards the end of the ice age actually. And also you've got all of these glacial deposits here in green and yellow and purple that were left behind during the last ice age. That you can see it goes through Michigan, northern Ohio, and then it goes into Minnesota, Illinois, and then we also have some going even farther south from earlier part of the Pleistocene epoch, all the way down to Davenport, Iowa. We also see marrons. Yeah, I don't know if any of you all have been to Massachusetts. Massachusetts, you probably studied in history class, is where the Revolutionary War started with the Boston Tea Party and all that. Well, Cape Cod, Nantucket Island, and Massachusetts, they call it Martha's Vineyard, but I guess we'll call it Martha's Vineyard. These were all formed from glacial till from the last ice age during the Pleistocene. So Cape Cod, Nantucket Island, Martha's Vineyard were all formed from glacial till during the Pleistocene epoch. Also, during the ice age, since we had a regression, the continents extend much farther seaward. You can see here that during the Pleistocene epoch, all of these areas in light brown were above sea level. At the moment, the state of Alaska is separated from Siberia through this seaway called the Bering Strait, which is part of the Bering Sea, off of this Kamchatka Peninsula in the very eastern part of Russia. Well, during the Ice Age, there was a land bridge going between Siberia and Alaska. We're going to see that this is quite important because that led to the migration of mammals from Eurasia to North America and vice versa. So the animals on both sides could mix. And that includes humans. Humans also left Siberia and went to Alaska. The latest archaeological evidence indicates that the Native Americans are really Tibetans and Siberians who migrated across to Alaska and then further down south, all the way down to South America. The earliest archaeological evidence for the Native Americans is found right here. And so they migrated across during the Ice Age, the Native Americans. Isostasy. What does isostasy mean? Well, what it means is gravitational equilibrium. And here you can see something quite interesting. You can see these red lines, which shows you how much isostasy occurred since the ice melted at the end of the Ice Age. In other words, if you see 100, you can see 90, 80, you can see 60, 50, 40, 30. That's in meters. So what it's telling you is that right here, for example, the ground has moved up 100 meters since the Ice Age ended. Here, it's moved up 70 meters. Here, 60 meters. Here, 10 meters. A meter is about 39 inches. It's about, you can multiply by 3 to get feet. Bottom line is, what that tells us is that the ice must have been thickest here in around this body of water called the Hudson Bay. That's where the ice was thickest, because the land was pushed down by the ice, by thick ice, and then when the ice melted, the land rose back up because the ice was no longer pushing down on the land. That's what isostasy means. So right around here, the ice must have been thickest because the land has risen the most. Because back during the Ice Age, the ice must have been thickest right around these two areas here, around the Hudson Bay area. Another interesting thing about the Ice Age is we had these pluvial and proglacial lakes, pleistocene lakes. So these are, back during the Ice Age, as I mentioned before, the Earth was a lot colder. We had a global regression occurring, and the ice would melt and would feed all of these lakes. These are all all these lakes were Ice Age lakes that existed during the Pleistocene epoch, from 2.6 million years ago to 10,700 years ago. With all of the ice, let me show you how that works. So let's take a look at braided streams from glaciers, and let's see if we can get some pictures. So when ice melts, it forms all this water that comes out of the end of the snout of the glacier. Here you can see glacial till, and that's going to make a moraine. And then you can see these braided streams, that the water that forms at the end of the glacier, called the snout of the glacier, is called meltwater. And the meltwater feeds these braided streams. And these would form lots of these Pleistocene lakes. So bottom line is, out west we had a lot more lakes during the Pleistocene epoch. All that's left of these Ice Age lakes is just a tiny little lake here called Pyramid Lake. We have the Great Salt Lake, this little bit here. That's all that's left of those enormous Pleistocene lakes that existed from 2.6 million years ago to 10,700 years ago. Here you can see another remnant lake from the Ice Age. It used to go for miles and miles, hundreds of miles further than this during the Ice Age. The biggest lake was called Lake Bonneville, by the way, which was right here in the state of Utah. And all that's left of Lake Bonneville is the Great Salt Lake. It's all dried up. So the Great Salt Lake is so salty because over the last 10,700 years, the Earth has been warming up. And so the water evaporates and the water becomes saltier and saltier as the chemicals in there are concentrated. When I went on my field trip with Penn State University, we geology students could swim for miles and miles. You can't sink because it's salt water. It's a lot of fun. Don't forget the Great Lakes were carved out by the Ice Age. At the very end of the Ice Age, you could see. So what causes ice ages to occur? Well, what causes ice ages to occur is twofold. There's two hypotheses. The first is greenhouse gases, carbon dioxide mostly. And what removes CO2 from the atmosphere? Trees. So if you have less trees, the Earth is going to cool down because you have less carbon dioxide in the atmosphere. The other possibility is mountain building. When mountains rise, and if those mountains are made of limestone, limestone is made of the mineral calcite and CaCO3 chemically. And limestone, so limestone is made of calcium carbonate. And when limestone reacts with water, it makes H2CO3, which is basically carbonic acid. So the bottom line is that when limestone is uplifted due to mountain building, it removes more carbon dioxide from the atmosphere. So if you have more mountain building occurring, you could also remove CO2 from the atmosphere. If you have less trees, you remove less CO2 from the atmosphere, and you'll get global cooling. If you have limestone, it removes CO2. It'll also result in global cooling. So uplifting of limestone mountain ranges, like the Himalayan mountains, that could cause global cooling because there are hundreds of thousands of acres of limestones in the Himalayan mountains. So bottom line, the short-term reason why we have global warming, global cooling is greenhouse gases, carbon dioxide and methane. And we have less CO2 removed when we have less vegetation. We have more CO2 removed when we have more vegetation. So when we have more vegetation, we have more CO2 removed. And we have what? If we have more CO2 removed, we have global cooling. And if we have less vegetation, then we're removing less CO2, so then we get global warming. But there's another possibility is that, like I mentioned before, the uplift of the Himalayan mountains 10 million years ago when India collided with Eurasia. That would have uplifted lots of limestone, removing CO2, and that could cause global cooling too, when you have the uplift of limestone mountains. So, if we want the Earth to cool down, we have more vegetation or we have uplifting of limestone mountain ranges. However, the longer term reason why we have global warming and global cooling is Milankovitch cycles. What are Milankovitch cycles? Well, Milankovitch cycles were from a man named Milankovitch, and he suggested that the reason why we have global warming and global cooling over the long term is because of the way the Earth revolves around the sun. And there are three cycles. There's a 20,000 year cycle, a 40,000 year cycle, and a 100,000 year cycle. And for example, when the Earth rotates on its axis, this is the North Pole, here's the South Pole, it's tilted. The Earth is tilted. And therefore, so imagine a top, the old-fashioned top where you pull the string and the top moves. The top of the top is the North Pole, the bottom is the South Pole, right? And that line between the two, between the North and the South Pole, is the axis of the Earth. Well, there's a tilt between the axis of the Earth and the orbit of the Earth around the Sun. And that angle it can vary between 21 and 23.5 degrees. So when the Earth is wobbling as it revolves around the Sun, you know by now that it takes 365 days for the Earth to revolve around the Sun. That's why an Earth year is 365 days. It takes 1 year for the Earth to revolve around the Sun. Every 24 hours, the Earth revolves around its axis. So an Earth day is 24 hours. As the Earth revolves on its axis, that axis is going to wobble between 21 and 23.5 degrees relative to this the orbital plane of the Earth. And when the Earth wobbles closer to the Sun, the Earth is going to warm up. When the Earth wobbles so that the Earth, like at 21.5 degrees, where the Earth is a bit farther from the Sun, the Earth is going to cool down. Also, as the Earth revolves around the Sun every 365 days, that forms this bent circle, which we call the ecliptic plane. I'll spell that for you. So the ecliptic plane is this circle, which is not a circle, it's a squash circle, which we call an ellipse, is the shape. This ellipse is formed every 365 days as the Earth revolves around the Sun. Well, sometimes that ecliptic plane will wobble like this. And when it wobbles closer to the Sun, it's going to get warmer. When it wobbles far, so the Earth is farther from the Sun, the Earth is going to get cooler. And also, the shape of this ecliptic plane will change every 100,000 years. So sometimes the Earth will get warmer, sometimes the Earth will get cooler, depending on is the Earth closer to the Sun or farther from the Sun. So the tilt of the Earth's axis, the wobble of the ecliptic plane, and the change in shape of the ecliptic plane mean that we have warming and cooling cycles that occur every 20,000, 40,000, and 100,000 years. And when all three of these cycles, the 20,000 year cycle for the Earth's axis, the precession of the Earth's axis, the 40,000 year cycle from the wobble of the ecliptic plane, and the 100,000 year cycle from the change in shape of the ecliptic plane, when all three of those cycles work together so the Earth receives less sunlight, so the Earth is a bit farther from the Sun, that's when we get an ice age. That's it in a nutshell. You could take a whole class on Milankovitch cycles. There's a lot of math involved, but since you're in a first, second year college class, all you need to know for this class is that Milankovitch cycles are the long-term reason why we have glaciers. And it's due to the precession of the Earth's axis, that means the wobble of the Earth's axis, relative to the ecliptic plane, the change in shape of the ecliptic plane, and the wobble of the ecliptic plane, those 20, 40,000, 100,000 year cycles, when they lead to the Earth receiving less sunlight, that's when we get global cooling. Here you can see all that I've already explained to you, the change in shape of the Earth's orbit, or the ecliptic plane, the change in the Earth's axial tilt, and also the wobble of the ecliptic plane. That's what the Milankovitch cycles are about. On top of that, though, we have human activity, which is causing the global warming to accelerate since the 1860s, and that's primarily due to us adding more CO2 in the atmosphere from burning fossil fuels, oil, natural gas, and coal, and cutting down trees. And trees remove CO2. So both the cutting down of too many trees and the burning of too much fossil fuels has accelerated the global warming, which is causing the sea level to rise and It's causing all kinds of problems. Deserts to grow, so that formerly fertile farmland is being invaded by deserts, leading some countries to have starvation conditions. Tropical diseases are moving away from the equator up into north and south of the equator. And so we have to do something to reduce our consumption of fossil fuels. We have to do it in a way, though, that allows for our economy to grow. It's possible we could burn coal and natural gas and oil and capture the CO2 and store it underground until we can fully move to the green energy. Or we have to go to nuclear power. But there's no simple solution that works for everybody. It's all based on compromise. We're going to have to plant more trees and stop and encourage the Brazilian government to preserve the Amazon forest, because the Amazon forest removes more CO2 than any place on planet Earth. That's the only way we're going to slow this global cooling. We have to use less energy if we can, make vehicles more fuel efficient, and insulate houses so we use less energy until we can get through this hump, so that someday we can move to affordable green energy. So that's the end of that chapter, and I'll have more for you in the next video.